this. So here are the myelin sheets. The myelin sheets are laid down in sections. They don't touch each other. The way that a myelin sheet is formed is by a Schwann cell. Think of a Schwann cell as looking like a pancake, or like this sheet, okay? And the Schwann cell will actually grow, and as it grows, it wraps itself around the naked axon, like this. And then the next Schwann cell will leave a space between it and wrap itself like you're wrapping a pancake around a wire or something like that, okay? And so this is one Schwann cell that made this myelin sheet. A different Schwann cell made this one, and all of these are made by different Schwann cells. Schwann cells do this if this neuron has a part of it, usually the axon, that's outside of the brain or the spinal cord, okay? And so Schwann cells myelinate the neurons, axon processes of neurons that are outside of the central nervous system, outside of the brain and the spinal cord. On the other hand, if this neuron was completely within the brain or the spinal cord, that means it belongs to the central nervous system. And instead of Schwann cells forming the myelin sheets, there would be oligodendrocytes that would form the myelin sheets, okay? Now, what that does is it will allow the action potential to be conducted even faster than usual. All right, let's suppose we're looking at an unmyelinated axon. Now, the action potential, remember that it's the spread of the action potential that represents the movement of the electrical part of an electrochemical impulse. As long as the electric part of the signal is traveling within the neuron, it's traveling by electrical changes called the action potential. But once that action potential reaches the end of the axon, there is a space, and then the next cell. That, what do we call that junction between two neurons? That would be the synapse, okay? And so there's a space called a synaptic cleft that the action potential cannot jump across. Notice that what causes the action potential is the opening of sodium channels, closing sodium channels, and opening potassium channels. That is a membrane function. Without membrane, you can't have an action potential, okay? Because an action potential is caused when the sodium channel is opened by a stimulus, open enough to pass threshold, sodium flows in, and you get this part of the action potential. Sodium channels closed, potassium channels open, and as potassium rushes out, you get the repolarization part of the action potential, like so. And so you have to have sodium and potassium channels to have an action potential. And to have those channels, you have to have cell membrane, okay? There is no cell membrane across this space. And so an action potential cannot jump across the space between neurons. That's when chemicals will be released from the tips of the axon. Okay, and if that chemical, third question, if the chemical that's released onto the next axon opens sodium channels first in the next axon, is that chemical transmitter acting as an excitatory or an inhibitory neurotransmitter? Excitatory. But on the other hand, if that chemical opens either potassium or chloride channels first, then it is acting as an inhibitory neurotransmitter, okay? But now, the electrical part, the spread of the action potentials is like knocking over dominoes. once the first action potential occurs, the electrical change that it creates opens the next set of sodium channels nearby, and the next set of sodium channels, and the action potentials keep getting created over and over and over again. And it's the creation of new action potentials that represents the spread of the electrical part of an electrochemical impulse. Okay? Now, what has that got to do with saltatory conduction? Well, if this axon was not myelinated, let's say that the fastest that the action potentials can create the next one and the next one is this fast. Okay, that's the speed at which new action potentials can be created. You think of it in terms of knocking over dominoes, that's how fast one domino falls, knocks over the next one, knocks over the next one. And as the dominoes get knocked down, that represents the action potential moving down the axon. Okay? Sodium channels open, the domino falls, and starts to knock over the next one by opening up the next channel. But the domino has to reset again. It resets by potassium channels open. But when the potassium channels open, the domino rocks a little bit, but returns to normal. And then when it falls and knocked over the next domino, that's the next action potential. And like as the dominoes fall, that is the electrical part of the impulse travel. Okay. Now, if the falling dominoes, if the new action potentials can only happen this fast, then imagine if this was not myelinated, the dominoes would have to fall at every point in the membrane. And it's gonna take a long time before the knocking over of the dominoes reaches the tip of the axon if this is not myelinated. So that's going pretty slow in terms of it moving down the axon. But now, let's keep the same rhythm. New action potentials are created every time this strikes. Okay? So instead of going point by point by point by point, the action potentials only happen at the nodes around here. So it goes like this. So the impulse is jumping down the axon and therefore moving much faster than this. You get the point. And so that's the function of the myelinating, the myelin sheaths, to allow faster impulses to be produced. All right,